In section 2.4, we're going to talk about the role of derivative in the real world. So we're going to look at something in the field of actually physics and dynamics. It has to do with motion of a moving object along a coordinate line. So the coordinate line is simply like your number line. That's what we call the coordinate line. And the kind of movement we're looking at along the coordinate line is a kind of a back and forth movement, okay, along a line. This is called a rectilinear motion that we're looking at in this section. So what I have here is kind of a drawing of how this motion is going to take place along the coordinate line. So if you can kind of see here, I have, let's say an object is at point A and then it moves towards point B. So initially S here is the position function. So at t equals 0, let's say the position is at point A. That's the beginning of the movement. And then this object moves to the right, and how far it goes to the right is a function of time. That's what f of t is. But it's important that S here is a position function. Okay, so what we have in the beginning is actually our first definition. And what you're looking at is definition of velocity. So we're going to define velocity. Remember, velocity is change in displacement over change in time. So in this fraction, ds, the numerator of this fraction is the change in position, and dt is the change in time. So the ratio of those two gives you the velocity, and of course both of those are a function of time. And that's what the definition reads. S is a function of time, and f is the position of the body on a coordinate line, and the velocity is given by that. And the velocity, because it's a rate of change, so that means it's the derivative of the position function. That means the change in the position over change in time, and that is why we use the prime notation. That turns out to be the derivative of the position function. Okay, now so I have here vt is our velocity function. Now something that's important here that we're going to note is the following. Now velocity is a vector quantity. Okay, now we don't do any vector analysis in Calc 1. You do all of that in Calc 3. But for now, enough to kind of get a point across here. The velocity is a vector quantity. So that means, as being a vector, it has both magnitude and direction. So this would be like the magnitude of the vector is how long it is, and the direction, of course, the arrow points to the direction. So I could have a vector quantity like this, I could have it like this, could have it like that. See, these are all vector quantities. Now, velocity is a vector quantity. Now, what's important for us here is the direction. If the velocity function turns out to be positive, that means on the coordinate line, the interpretation of that is that the object is moving to the right. And if the velocity is negative, therefore the object must be moving to the left. Remember, why to the left? Because the direction, a negative direction, it looks like this. That's a vector that's going in the negative direction. This is a vector going to the positive direction. So here velocity is positive, here velocity is negative. Now the magnitude of that velocity, how can velocity be negative? Again, the positive or negative orientation has to do with direction of the movement. Now, if we don't care about the direction, then we're talking about the speed. Now, a lot of us kind of think about speed indirectly, right? When we say, well, how fast were you going? Well, my velocity was that. Or we're talking about speed velocity in a meaningful way in the same context. But technically they are different. So if it's the speed that you're thinking of, then we need to talk about the absolute value of the velocity function. And that gives you the speed. Now speed has only magnitude but no direction. Okay, so with the speed, like how fast were you going? I'm doing 60 miles an hour. if I'm going north, it will be positive. If I'm going south, it will be negative. But as long as you don't care about whether I'm going north or south, you say, well, how fast were you going when the police gave you a citation? I was doing 80 miles an hour. That's just the speed without the reference to a direction. Now, a couple of more ideas here. One of them is that of acceleration, and the other one is a jerk. Now, the acceleration is the rate of change of velocity. So, to go back to the root, the rate of change of position per unit of time, that's velocity. Acceleration is the rate of change of velocity per unit of time. So let's say your automobile is at rest, you're behind a red light. The light turns green and you press on the gas and you speed up and you go from 0 to whatever you're going, 30, 40, 50 miles an hour. So how fast is your speed changing, your velocity changing in this case, per unit of time? That is your acceleration. Okay? And that's what AT is. Now, so AT, because it's the rate of change of velocity, so that would be V prime for us. And because V prime, V itself is in terms of F prime T, so we use the second derivative of the position function in order to come up with the acceleration with respect to time. So we can say AT is V prime T or F double prime T, the second derivative of position function with respect to time, or the first derivative of velocity with respect to time. Now, the third derivative of the position function, that's the second derivative of the velocity and the first derivative of the acceleration. The jerk is that initial jump. Like, for example, again, suppose your automobile is at rest and all of a sudden you step on the gas pedal and you're kind of whiplashed. Okay, that's the jerk that we're talking about. Jerk is the rate of change of acceleration now per unit of time. Okay, so anytime you find yourself being whiplashed in a car as you speed, then that's the idea of a jerk. A rate of change of acceleration per unit of time. Okay, so now let's kind of put this all together and see how we're gonna do this in exercises. So here in exercises 1 through 8, I was going to do a couple of these with you. I'm going to take a look at exercise number 2 and exercise number 6. Okay, so in exercise number 2, S of t is the position function of a body moving along a coordinate line. S of t is measured in feet. Remember, that's a position, so it's in feet. And time t is typically in seconds, and we assume t has to be greater than or equal 0, right? We don't have negative time. The question is, find the position, velocity, and the speed of body at indicated time. Okay, so question number 2 here, let's begin with that one. Problem number 2, the function is f of t. Is actually they use S of t. In the definition they use f. That's fine. They use f of t, and now they see. Let me go back up here. We're talking about the velocity functions. See, s is a function of t. F is the position function, but in the exercises they actually use S of t, which is fine. So that's what I'm going to use. So for number 2, the position S of t is given by 2t cubed negative 3t squared plus 4t plus 1, and t is equal to 1. Okay, now the question asks us to find position, velocity, speed at indicated time, and t, indicated time here is t equal 1 second later. So s at 1, you just plug in a 1 for t. That's going to be 2 times 1 cubed, negative 3 times 1 squared, plus 4 times 1 plus 1. And that gives me 2 minus 3 plus 4 plus 1, and all of that would be 4. units are in feet. So it's 4 feet at t equal 1. It's the position, on the coordinate line is at 4 feet away. Okay, so now if I draw a sketch here, this is s of t, position at any given time. S at 0, that means initially, where is this object? This is number line 0. S at 0 is at 1. You plug in a 0 for t here, you get a 1, right? So initially, the object doesn't start at coordinate line at 0. It actually starts 1 feet away from 0, from some reference point. So it could be a feet from the house, it could be a feet from the start line, whatever. And then 1 second later, 2, 3, 4. So S at 1 is 4 now, right in here. You see the object moves from here to here in the matter of 1 second. This is at t equal 1. So looks like it must have gone in that direction. So let's find the velocity of that moving object at t equal 1. Means how fast was the velocity. So vt is s prime t, and that's going to be 6t squared, negative 6t plus 4. And that's in feet per second. This is for any time t after it takes off. Now they want to know velocity 1 second later, so that's going to be s prime at 1. Again, you put 1 for t, negative 6 times 1 plus 4, and that number should turn out to be 4 feet per second. Okay, now because velocity is positive, so that means it's moving to the right. You see that? So it's moved to the right. What was the speed? Well, the speed is absolute value, right, of the velocity. So it's absolute value of velocity at 1. And the speed, of course, here absolute value of positive remains positive, but imagine if the moving object was moving to the left, velocity would have been negative, but its speed would have been positive. So that's what that is. And that's all we got to do for this one. Okay, let's look at number 6. In exercise number 6, here directly above where I'm writing, s of t is t squared over t squared plus 1. And this time at t equal 2 seconds later. So for this one, again, that's just me, s at 0. I like to know where this object starts at. So this is the beginning, 0 feet. So starts at exactly 0 on the number line. Okay, and then let's find at t equal 2 seconds. So the position s at 2 is going to be 2 squared over 2 squared plus 1, which is 4/5 feet away from where it started. Now the velocity vt is going to be s prime t, and for this we got to do derivatives. So I'm going to do using the quotient rule for derivatives. Okay, so in doing the quotient rule, I have square the denominator, that's t squared plus 1, and repeat the denominator times the derivative of the numerator is 2t, negative numerator times derivative of the denominator is 2t. So this will give me factor 2t from the top. I get t squared plus 1 minus t squared divided by t squared plus 1. Oh, and I got to square the denominator, right? And there you go, squared. The numerator, we got opposites, so this is going to be 2t over t squared plus 1 squared. Okay, so that's going to be the velocity at any given time. And now for 2 seconds later, so velocity at 2 seconds later is going to be 2 times 2 squared plus 1 quantity squared, and that's going to be 4/25. So it's not fast, huh? 4/25, that's almost 4 divided by 4/20th, that's 1/5, right? So it's not even 1/5. Okay. But it's positive nonetheless. So the object is moving to the right. At that point, the velocity of that moving object is 4/25 feet per second. Okay, that's what that is. And it is moving because it's positive, so it's moving to the right. Okay, and we're good with this one. All right, and then let's take a look at our next problem here. So for this next one, I'm going to do number 12. So in problem number 12, exercise number 12, st is the position function of a body moving along a coordinate line, t positive, st measured in feet, and t in seconds. Most of these problems start out this way. In part A, determine time or times and the positions when the body is stationary. Okay, when the body is stationary, so for example, just to show you, here's from point A, this is point B. So when it moves to this from left to right, I'm moving from left to right, this is not a stationary. Now remember, we're talking about movement along the coordinate line, so that means we only can go forward, backwards, forward, backwards. That's the kind of movement. Okay, it's kind of movement like the old printers before the laser jets. There were daisy wheels printers. That they would move back and forth along a line to print on the page. So anyway, and I'm going to the right, and here the velocity is positive, right? Now, and then let's say at this point B, once I hit point B, I'm going to go back towards A, so velocity is negative now, right? Well, for an instant in time, right in here, as soon as I hit B and I return, velocity is going to be 0. Because if it's not 0, I'm going to keep going to the right, aren't I? It has to become 0 and then negative so I can go back. So the stationary points, make a long story short, stationary points are points where velocity is 0. Okay, let me just write that. Stationary. That implies velocity equals 0. Okay, so I need to find the velocity function and set it equal to 0. S of t is 1/3 t cubed negative 3/2 t squared plus 1. Velocity at any given time is going to be the derivative of the position function, and that's going to be 1/3 times 3t squared negative 3/2 times 2t. And that's going to give you just t squared minus 3t. Okay, now we're going to set it equal to 0 because we want to find the stationary point. Okay, this is stationary, st, stationary point is right here. This is where the point of where the velocity is 0. So I can factor this, tt minus 3 equals 0. So at 2 instant of time, the velocity is 0. First, initially when the object actually starts to begin to move. So at t equals 0, it's stationary. Velocity is 0. And then 3 seconds later, it's also 0. 3 seconds later. So that answers part A. The answer to part A is that. Now, in part B, so we answered this part. When is the body in the positive direction? In the negative direction? Okay, so to do part B, we need to actually come up with a sign chart. This is actually velocity. This is a number line, 0. Okay. Now, of course, because t is at least 0, so your number line really just starts from, there we go, starts from 0 and moves forward. And let's say this is 3. Okay, now what I need to do is this. at 3, we're going to look at the sign of the velocity, because remember, that's the stationary point, neither positive nor negative. So we want to know, is it positive, negative here, or is it negative transition into positive? The velocity, that is. That's what we want to determine. So I'm going to pick a test point, like t equal 1. And then velocity at 1 is going to be 1 times 1 minus 3, right? I'm looking at that expression. 1 times 1 minus 3, and that's going to be negative 2. Now, negative 2 is less than 0, so it's moving to the left, so that means velocity is negative. And then you can pick a test point like 5 here, for example, anything you want, t equal 5. Velocity at 5 is, again, I'm going into here. That's 5 times 1 minus 5, and the velocity, let's see, at 5, it's going to be, oh, what am I doing? Sorry. 5 minus 3, not the 1 minus 5. Okay, because t is 5. And that's 5 times 2, or 10. Don't worry about the magnitude of that. All we need is the sign. Positive, so it's moving to the right. Left on top, right on the bottom. That's positive. So velocity is positive, velocity is negative, and that answers the part B. When is the body in the position? Let's see. When is the body moving in the positive direction? So positive means to the right, correct? So for t between 3 and infinity, it is positive. And then between 0 and 3, it is negative. Because the question again asks, when is the body moving in the positive direction, in the negative direction? And we did that. Now, next part, the question reads, part C, sketch a schematic showing the position of the body at any time. So for this one now, our schematic, this is a number line. Okay, so this is like ST, the position at any given time. Remember, at t equals 0, that's the lowest, and that's the minimum for time. Here's 0 on the number line, 1. At t equal 0, the position we found was at 1, right? At t equals 0. Do I have it here? No. Anyway, s at 0, the position at 0 is 1/3, 0 cubed, negative 3/2, 0 squared plus 1. I'm looking at this function. That's the position. And that's going to give me 1. So at t equals 0, this is where the object begins. This is at t equals 0. Okay. And then it moves to the left, right? Remember, between 0 and 3, the object is moving to the left. At 3, s at 3 is where it is along the coordinate line. So s at 3 is going to be 1/3 times 3 cubed, negative 3/2 times 3 squared plus 1. And this is going to be 9, negative 27/2 plus 1. And using LCD, this is going to be negative 7/2, right? 18 minus 27 plus 2. You need LCD. LCD is 2. Negative 7/2, which is negative 3.5 feet. So it actually goes to 1, 2, 3, 4. This is negative 7/2. And then remember, at t3, velocity is 0, right? The transition from left to right. So here's what I'm going to do. This object's moving to the left. And then it's going to turn. And it's going to continue on to infinity, right? In that direction. So that's the orientation of the direction of the movement. And this point is t equals 3. Okay, and that's what that is, at t equals 3. And that's the schematic they're talking about. Notice what I have drawn here, this curve that I have drawn, it's not the path. It's not the path of this moving object. It's just how the position is changing. There you go, a little better. So just wanted to point that out. And I think we were good with this exercise now. Okay. Let's take a look at another exercise. In this next example, we are on number 7 through 20. Let's take a look at actually exercise number 20. So, in exercise number 20, the question is asking us, S of t is the position function of a body moving along a coordinate line, the usual stuff. Part A, we want to find the acceleration. Now, when is acceleration 0, when is positive, when is negative. So the sign chart of acceleration is going to tell us about that. So we're doing number 20. S of t is t cubed over t cubed plus 1. Okay. Now, S prime t, we're going to use the quotient rule. So that means we're going to square the denominator, that's t cubed plus 1 squared. Repeat the denominator, derivative of the numerator, minus numerator times derivative of the original denominator, not the one that we squared it because of the quotient rule, not this one. Okay, and so S prime of t is going to equal to, now here I can factor 3t squared from the numerator. That gives me t cubed plus 1 minus t cubed divided by t cubed plus 1 squared. And the t cubes on top are opposite, they add to 0. So our first derivative is going to be 3t squared over t cubed plus 1 squared. That's our first derivative, right? This is actually the velocity function. Now, the question is asking for the acceleration, right? So to find acceleration is when we do second derivative of the position function. So AT is first derivative of the velocity and the second derivative of the position function. So that means I got to take the derivative of a velocity function, the one that we just found. Now, at some point, I'm going to take the derivative of the denominator, right? Because we're doing the quotient rule. And look at this denominator. Okay, for this denominator. Again, if I want to find the derivative of that, this is what I'm talking about. There. We want to find the derivative of this. So if I use the power rule, bring 2 in front, write it as 2 times t cubed plus 1. That would be, that's part of it, but it's not quite the answer. And the reason is because this function is a composition function. It's a function within a function. What I mean is this. For example, I see this as x squared. Okay? The derivative of that is 2x, but then x itself is t cubed plus 1. So that's the composition I was talking about. So anytime we have function composition, we cannot end it with just the power rule. We need more than that. In fact, we will learn how to do derivative of function composition in a couple of sections down from now, 2-3 sections from now. We need to know about chain rule in order to find derivative of composite functions. So for now, I'm going to mark this incorrect. So how are we going to do it again as of right now? We don't know about chain rule right now. So how am I going to do this? Well, the easy way is to expand the binomial. You see that? Write it as first one squared plus twice first by second plus second term squared. So there you go. And then take the derivative of that. So that's what I'm going to do. Okay? Therefore, S double prime is going to be, we're going to square the denominator, right? The denominator is t cubed plus 1 squared, and yet we square it again, right? We're looking at this denominator. And then we're going to repeat the denominator. When we repeat the denominator, it's t cubed plus 1 quantity squared, right? Times derivative of the numerator. This is the numerator. That's going to be 6t minus the numerator times the derivative of the denominator. So keep in mind our denominator is this, right? So I'm going to find the derivative of t to the 6 plus 2t cubed plus 1. And that derivative is going to be 6t fifth plus 6t. That's it. Derivative of 1 is 0. See how easy that was? And you can see why now this is not the correct answer. If you go off of that, you get 2t cubed plus 2, which is in 6t fifth plus 6t. Okay, and what do we do next? Next, let's factor t cubed plus 1. Okay, 6t to the fifth. Let me do this. This is the derivative. Derivative is going to be 6t fifth plus 6t squared. 6t squared. Good thing I caught myself. Right? Plus 6t squared. Now, I can factor 6t squared from this derivative, and that makes it t cubed plus 1. Now, once that's t cubed plus 1, then I can factor the expression. Okay, I can go t cubed plus 1 squared, not doing anything yet, negative 3t squared, and now I'm going to write the factored form, which is 6t squared times t cubed plus 1 divided by t cubed plus 1. This would be to the 4th power. Now, there's t cubed plus 1 in the numerator and in the denominator, right? So we can cross out that t cubed plus 1, and one of the two in the front and one in the bottom. So in effect, I crossed out a factor of t cubed plus 1 from the top and the bottom. So in the numerator, I have 2 of them. See, in here I had 2. I got rid of one of them. I still have 1. So it's going to be t cubed plus 1 times 6t, negative 3t squared times 6t squared. That's going to be negative 18 t to the 4th. Okay. And then over t cubed plus 1 cubed. So hopefully you followed what I did there. And then we can now finish this off, and let me distribute to the binomial. This becomes 6t fourth plus 6t minus 18t to the 4th, all over the denominator t cubed plus 1 cubed. Okay. So the acceleration at time t is going to equal to we're going to combine like terms. 6 minus 18 is going to be 6t minus 12. 6 minus 18 is 12t to the 4th over the denominator t cubed plus 1 cubed. Then I can factor the numerator 6t, that makes it 1 minus 2t cubed, right, over the denominator t cubed plus 1 cubed. Now we're going to set this equal to 0. This is the acceleration at any time. But again, the question is asking, find the acceleration of the body, which we just did. And when is the acceleration 0, positive or negative? Just like with the velocity. But this is the acceleration function right there. Okay, now if I set it equal to 0, then I'm going to get the parts where acceleration is 0. Now, in a fraction, the only way a fraction can be 0 is if the numerator is 0. Okay, and from this we get t equals 0 by 0 factor principle, or 1 minus 2t cubed is 0. That means 2t cubed equal 1, and therefore t cubed is 1 over 2, and t must be cube root of 1/2. And cube root of 1/2, we can rationalize that denominator, right? 1 over cube root of 2. So if I multiply by cube root of 4, I have rationalized it. And this becomes cube root of 4. Cube root of denominator 8 makes it 2. And there you go. So those are places where the acceleration is 0. Okay. Okay, now let's actually create our sign chart of the acceleration. And this time, this is the acceleration. This is AT. Now the units on acceleration, because it's the rate of change of velocity, so it's feet per second for the velocity, and then the rate of change means you divide it again by change in time. So it's going to be like feet per second, which makes it feet per second squared. Those are the units of acceleration. Now, at t equals 0, for all of these, t cannot be negative. So t equals 0, acceleration is 0, a equals 0. And then at t equal cube root of 4 over 2, well, cube root of 4 over 2, think of it, cube root of a half, it was cube root of a half before we rationalize it. So cube root of a half is going to be a very small amount. It doesn't matter. There you go. Right in here, I'm going to call this t equals cube root of 4 over 2. Whatever that number is. We don't need a calculator. The acceleration is 0 here again. So the object is moving from start, then it's speeding, and then it's probably acceleration 0 at some time later. That's when the velocity becomes constant, because the derivative of constant is 0. So in other words, let's say for the first half a second it accelerates, and then it's going at a constant velocity where there is no acceleration. It's kind of like moving on a cruise control. You're cruising at a certain speed without accelerating. Okay, so our sign chart now, I'm going to pick a number, it doesn't matter, anywhere in here and in here, because the factors and the, let's see, for acceleration. Oh, and the other part of this, let me backtrack a little bit here. Okay, what I've said right now is correct. I just need to tell you a little more. Okay, I'm going to make this to be my 0 actually. All right, and this is -1. And this would be cube root of 4 divided by 2. The reason I have -1 here is because in this acceleration function, this is a rational function. To find the zeros of this rational function, we look at the numbers that make the numerator and then denominator 0. So what makes t cubed plus 1 0? Well, t cubed is -1, so t is -1. So that -1 is actually there. And at that point, by the way, you get division by 0. Okay? But remember our restriction. To begin with, we said, right in here, t is greater than or equals 0. So we aren't allowing for negative t values, right? So in other words, we don't have to worry about this portion of our work. The reason I mention this is because later on, for another topic, we're going to actually include what makes the top 0 and what makes the bottom 0. But for now, our threshold, the lowest t can be is 0. So that's why initially I didn't even bother with that. All right, so we're back to what I was doing earlier. I'm going to pick a test point here, and you can pick a test point here. Now, because in the numerator, your factors are not repeating, so I don't have, for example, t squared, and I don't have two factors of 1 minus 2t cubed. There's only one of them. So pick a test point like 1 here, plug it into that, and you get 6 times 1. 1 minus 2 times 1 cubed. This is going to be 6 times 1 minus 1. Okay. 1 minus 2 actually. The 1 cubed is 1 times 2, and that's negative 6, less than 0. So the function, this rational function is going to be negative, right? And then also in the denominator, in the denominator also, because it's the whole function, the rational function. So that's just the numerator, right? Let me fix that. I'm putting in 1 in the entire thing, so it's 1 cubed plus 1 quantity cubed. That's my test point. And the numerator is going to be 6 minus 12. Denominator is going to be 2 cubed. So that's negative 6/8, less than 0. So the sign is negative. And over here it's going to be positive. You can pick a test point if you like. Something less than this number, whatever that is on the calculator. Or again, I'm going to go with plus because I don't have repeated factors in that rational expression that repeat in an even number of factors. Anyways, so acceleration is negative here and acceleration is positive in that segment. Okay, and the answer to the question, acceleration is positive from 0 to cube root of 4 over 2. And the acceleration is negative as we go from cube root of 4 over 2 to infinity. There, that's the answer to that question. And that's it. A long problem, huh? But we answered the question. Hopefully you followed what I did, and you can always rewind the video and watch it again. Alrighty, let's take a look at this one now. In this exercise, an application. Okay, we're still in that section. This is the motion of a projectile. A projectile is fired from a cannon located on a horizontal plane. If we think of the cannon as being located at the origin O of an XY coordinate system, then the path of the projectile is given by that function. And XY are both measured in feet. Now, in parts A through E. Part A, find the value of angle of elevation of the gun. Okay, so if you actually look at this portion, we're doing part A. In this portion, we're going to find theta here, right? Now, the angle of elevation, I can think of this as a change in y over change in x, right? And that's going to be the angle of elevation. Well, change in y over change in x, isn't that the slope of a tangent? Slope of a tangent, which is f prime of x, right? Or y prime. They use y. This is y prime. So I just need to find the slope of a tangent, and that will help me find the angle theta. So how do I find the slope of a tangent? It means I need to find the derivative. This is the function y. The derivative is going to be the derivative of root 3x is just root 3, negative 1 over 400, constant multiple, and derivative of x squared is 2x. Okay, so that's going to be root 3 minus 1 over 200x. That's the slope of the tangent, right, at any point. Now, at the origin, this is the origin. And that's when x is 0, right? Here x is 0. So let me write that. At origin, x is 0. So the slope of a tangent at 0, therefore, is when you plug in a 0. for x, and that's going to be times 0 or square root of 3. Slope of a tangent is root 3. So now we can actually draw our triangle, and this is theta. Slope is change in y over change in x, right? A rise over run. So root 3, I can think of root 3 as root 3 over 1. That will give me a rise and a run. So the hypotenuse of this triangle is going to be root 3 squared plus 1 squared, 4. And square root of that is going to be distance d, the hypotenuse, or 2. So this is a 1, 2 square root of 3. It's one of your special triangles from trigonometry, right? And in fact, that's your 30, 60, 90 triangle. That angle is 30, and theta is going to be 60 degrees, right? Or you can also do it this way to get that 30 degrees. I know that we want to find theta, right? We want to find theta. So if I get tangent of theta in this triangle, that's root 3 over 1. So theta is going to be the arctan of square root of 3. And that ties in with your trigonometry now. Now the arctan of root 3 is going to be 60 degrees, or pi over 3. Now tangent, of course, is positive, right? Tangent is positive in the first quadrant and in the third quadrant, right? Remember, this is 60 degrees, and so is this one. The reference angle is 60, but actually tangent is positive in the first and in the third quadrant. So why do we not choose it here? And that has to do with the range of tan inverse. If you recall from your, again, this is all from your trigonometry, not calculus. The range of tan inverse is from negative pi over 2 to pi over 2. So the measure of the angle that we actually are looking for is going to be pi over 3 inside of that range of inverse function. This is from your trigonometry. Okay, and this, again, it's not calculus. All right, so we answered that part. The answer to part A is 60 degrees or pi over 3. In part B, what are they asking in part B? In part B, at what point on the trajectory is the projectile traveling parallel to the ground? Now, parallel to the ground on the graph. Now I'm on the graph. Right there. That's running parallel to the graph. So it's going to be the point where the slope of a tangent is 0, right? Okay, so that's what we need to do. So for part B, we're going to set y prime equal to 0. And remember, we found y prime earlier. That was root 3 over root 3 minus 1 over 200x. We're going to set it equal to 0. And this add or subtract square root of 3 from both sides, multiply by 200. We're going to get 200 rad 3 feet. So there you have it. That's going to be at what point? That means 200 feet out. So if I go on the graph, what we found is here, 200, not 200 feet, 200 root 3 feet out. Now it says point, right? At what point? So we need to find the y. X comma y. Every point has an x and a y. We found the x. How do I find the y? Well, to find the y, we need to plug in into our function, right? Y is equal to square root of 3x times, that's x, square root of 3x minus 1 over 400 times x squared, which is 200 root 3 squared. Okay. And this will give me root 3 is just 3 times 200 is 600, right? 200 root 3 squared, 200 squared is 40,000. Divide by 400. It's going to be 100. And root 3 squared is 3. 3 times 100 is 300. The answer is 300 feet. So the coordinates are 200 root 3 and 300. So at that point, the trajectory is traveling parallel to the ground. In part C, what is the maximum height attained by the projectile, where the maximum height is the place where the slope is 0. In this case, that reaches the top of the curve. So max height is going to be 300 feet. That's just this number. Okay. That's the y value. In part D now. In part D, what is the range of the projectile? That is the distance OA. The range of it, they're talking about how far it's going to go before it lands. This is what they talk about, the range. Okay, so the range of the projectile, I need to find the coordinates of point A, don't I? And the x component gives me that. So for part D, for the range, okay, at point A, we know that y is 0, right? Because it's touched the ground, right? So we're going to set root 3x minus 1 over 400 x squared equal to 0 and solve for x. Factor the x out, we get root 3 minus 1 over 400 x equals 0. And then from this we get x is 0 by 0 factor principle, or root 3 minus 1 over 400 x is 0. And subtract root 3 from both sides, multiply by 400, we get x is equal to 400 rad 3 feet. That's the landing point, right? So again, the trajectory goes like this. This is point A, which is 400 root 3, and starts at O at 0. And there you go. Okay, and we found this point. The peak happens at 200 root 3. Okay. Now, that answers part D. So the range is going to be 400 root 3 feet. Again, range means, like how far, what's the range of the movement? It goes 400 root 3 feet out from starting from the shooting point. Cool. We got one more, last part, part E. At what angle with respect to the x-axis? With respect to the x-axis, this is the x-axis. Means this angle. That's what they mean. Okay. At what angle with respect to the x-axis does the projectile hit the ground? Looking at that portion of the graph. Okay. So to do part E, again, this is how it's coming down, and this is x. Again, if I draw the tangent line at that point, okay, once it hits the ground, it's going to hit it like that. That's the tangent line. I need to find the slope of a tangent line at A, and this is the angle now. Call it alpha, since we already used theta. This is the angle alpha that I want to find. What is the measure of angle alpha? So let's take a look at the slope of a tangent when x is, remember, at that point x is 400 root 3. Correct? So the slope at A is going to be, again, dy over dx, or the derivative of the function. We want to evaluate it at 400 root 3. So the slope we found it to be earlier, the slope of a tangent was root 3 minus x over 200. That was the slope of a tangent. Evaluated at x equal 400 root 3. That means you just plug in that number in for x. So this is going to be root 3 minus 400 root 3 over 200, right? And that's going to be root 3 minus 2 root 3. Divide the 200s out. And those are like radicals, negative root 3. Okay, now let's analyze this one. Again, that's the slope of a tangent at A. So here's how we're going to draw our triangle. This is negative root 3, right? The fact that the line's orientation is the way you're looking at it is going like this. That's why the slope of a tangent is negative. It shows you the orientation. Now, I need to build my triangle here. Remember, the slope, we found the slope of this line to be negative root 3 between here and this point. Now, this is angle alpha we want. Okay, so let's call this angle beta. Tangent of beta is root 3 and negative 1 here, right? I'm rewriting negative root 3 as root 3 over negative 1. Okay, so this is the rise and this is the run. My run is negative, so I went from point A to the left. Okay, that's why I'm here now. So tangent of beta is root 3 over negative 1. So beta is going to be arctan of root 3 over negative 1. Now, this is going to be a special triangle. Again, we just did it up earlier for part A. This is your 1, 2, root 3 triangle, right? So beta turns out to be negative 60 degrees, right? Because tangent is negative. And again, tangent is negative. If you look at the range of tan, tangent is negative in the fourth quadrant. And this is what we just found. Okay, we found this is 1, this is negative root 3. The reason I have it this way is to adjust for my triangle. Notice my triangle is on the left, but I'm drawing something on the right here. Okay, so the measure of this angle again is going to be 60 degrees, and it's negative because it's within the range of inverse from negative 90 to 90. So beta is negative 60, right? Alpha and beta are supplementary angles, so that means their sum has to be 180 degrees. Therefore, alpha is 180 minus beta, and that's 180 and minus 60 degrees. Okay, and so it's going to be 120 degrees here, right? And I'm looking at beta here being 60 degrees. The negative 60 is for this triangle, because if you do it on the calculator, it's going to give you negative 60 degrees, right? So we need to kind of adjust for the geometry of this exercise. So that answers the question: at what angle it strikes the ground relative to the x-axis means this is the x-axis, 120 degrees relative to the x-axis. Okay, and with that we are done with this section. So again, one interesting application, but the earlier ones, I guess you were okay with the earlier ones, right? Those are just pretty mechanical process. And with that we are done with this section.